Most of the time we think of weather as just a bit of rain or sun, right? But every so often, the atmosphere decides to show us what it's really made of. So, what is actually going on inside a hurricane or a massive thunderstorm? Today, we're going to break down the physics behind the most extreme weather on our planet.
I think this quote just gets right to the heart of it. These aren't just weather events, they're a raw display of energy. A reminder that we live inside this incredibly dynamic system that, well, occasionally needs to let off some very serious steam. So, what even is extreme weather? When you boil it all down, it's about one thing: imbalance. See, when energy builds up in one place faster than the atmosphere can gently get rid of it, it has to correct itself. And sometimes those corrections are, well, they're explosive. But listen, this isn't all doom and gloom. Most of the time, the atmosphere is actually pretty stable and well-behaved. This is all about understanding the incredible physics behind the exceptions, these powerful events that don't just happen on the other side of the world, but can shape the weather right here in the UK.
Okay, first up, the fast and furious stuff. Let's dive into the vents and twists of the atmosphere. We're talking thunderstorms and tornadoes. Honestly, the best way to think of a thunderstorm is as the atmosphere's own pressure valve. When you get too much heat and humidity building up near the ground, a storm is simply the most efficient way to vent all that energy upwards into the sky. It's just like a kettle letting off steam.
So how does it happen? Well, it all starts with this unstable, warm, moist air sitting near the surface. Something, anything, gives it a little nudge upwards. As it rises, it cools, and a cloud starts to form. But here's the secret sauce. As that water vapor condenses, it releases this huge burst of energy called latent heat, and that acts like rocket fuel, supercharging the updraft and creating those violent currents that really define the storm. So, what happens when you add a twist, literally, to that violent upward rush of air? Well, you can get a tornado. They're born from rotation deep inside the most powerful thunderstorms. If you have winds at different altitudes blowing at different speeds, it can create this huge spinning column of air, what's called a mesocyclone, and that can then tighten up, intensify, and drop right down to the ground. And get this, because this might actually surprise you. We tend to think of tornadoes as a purely American thing, right? From Tornado Alley. But the UK actually has one of the highest densities of reported tornadoes in the world for its land area. So, why aren't we seeing that same level of devastation? Well, it all boils down to intensity. UK tornadoes are typically much weaker, and they don't last very long. They're usually these brief, localized events, not the long-lasting giants that can carve a path of destruction for miles across the US plains. It's a classic case of frequency versus raw power. Okay, so let's scale up. We're moving from the fast and the focused to the truly gigantic. Now we're talking about the immense heat engines we call hurricanes and the massive, bone-chilling power of a blizzard. At its heart, a hurricane is basically a giant heat engine. It can only form over these really warm tropical oceans where the water is above 26 degrees Celsius, and it just continuously sucks up heat and moisture from the ocean, converting all that thermal energy into the absolutely staggering kinetic energy of wind and rain, all organized in that iconic spinning spiral. Now, the UK is way too far north for a true hurricane to survive. The water's just too cold. But that doesn't mean we don't feel their influence. We get the remnants, what are called ex-hurricanes. And a perfect example was Ophelia back in 2017. It traveled way up north, lost its hurricane status, but still slammed into the UK with powerful gales. And remember those bizarre orange skies? That was from Saharan dust it had picked up on its journey. All right, let's switch gears to the other kind of giant, the cold one. A blizzard isn't just heavy snow. The definition is actually super specific. It's a combination of three things. You need freezing temperatures, you need heavy snow, and, this is the crucial bit, you need strong winds that whip all that snow around, reducing visibility to almost nothing. If you take away the wind, you've just got a snowstorm. I'm sure many of us remember the beast from the East. It was a textbook example of how the UK gets its most severe snow. We had this intensely cold, dry air flooding in all the way from Siberia, and it collided with moist air moving in from the Atlantic. That clash created widespread, really disruptive snowfall that brought a huge part of the country to a complete standstill.
So we've covered the fast and the giant. But some of the most impactful extremes are the ones that creep up on you slowly. These are the persistent, slow burn events, like heat waves and droughts.
So what actually causes a heat wave? Well, it's all about high pressure.
A really strong, stubborn area of high pressure basically acts like a lid on the atmosphere, creating what meteorologists call a heat dome. It traps warm air, it stops clouds from forming, and it blocks any cooler weather from moving in. So the sun just bakes the ground day after day after day. The legendary UK summer of 1976 is the perfect case study. It wasn't just a brief hot spell, it was a crisis that just built and built for months because that high pressure refused to move. Reservoirs dried up, and things got so serious that the government actually appointed a minister for drought. But the way it ended is just as telling as how it began. You see, a drought is kind of like the quiet cousin of the heat wave. There's no drama of a single storm, just the relentless, cumulative effect of way too little rain over many, many months. Rivers get lower, reservoirs shrink, and the soil itself can become completely parched. And this is the dangerous paradox we saw back in '76. When heavy rain finally does arrive after a long drought, the ground is often baked as hard as concrete. It just can't absorb the water. So instead of soaking in, all that rain just runs right off the surface. It means the very event that ends the drought can tragically trigger a flood. So what's the big takeaway from all this? Why does understanding the mechanics of these things actually matter? Well, it's all about shifting our perspective from one of fear to one of respect. The really important thing to remember is that extreme weather isn't just random chaos. It's the result of this deeply interconnected system trying to find balance. A tiny shift in the jet stream or a patch of unusually warm ocean can start a huge domino effect, tipping a whole region from calm into chaos. Every single one of these events has a recipe. Thunderstorms absolutely need that powerful mix of heat and moisture. Blizzards need cold air and some kind of lifting mechanism. Heat waves need still, stagnant air. And once you start to understand these patterns, you can read the signs. And that's how fear starts to turn into respect, and respect turns into preparedness. And looking ahead, well, the science suggests that a warming climate is effectively loading the dice. By pumping more energy into the atmosphere, the prediction is that these extreme events could become both more frequent and a lot more intense. This, right here, is the perfect thought to end on. These events aren't good or bad. They aren't malicious. They are simply expressions of the raw physics of our planet. They're a display of the incredible power contained within our atmosphere, a system that is beautiful, sometimes dangerous, and is always, always changing right above our heads.